What is grease? Have you ever wondered how a massive mining machine can handle tons of load under abrasive dust, or how an airplane landing gear can survive temperatures of minus 50 degrees Celsius without freezing? The answer lies in an ancient invention perfected by modern science: grease. This seemingly simple substance is actually a highly sophisticated lubrication system designed to overcome challenges where ordinary oils fail. But after all, what is grease, and why is it so essential to modern engineering? Grease is not simply thick oil. It is a semi-solid colloidal system in which a thickener acts like a molecular sponge, trapping a base oil and additives. Imagine a network of microscopic fibers, usually metallic soaps such as lithium or calcium stearate, holding the liquid lubricant inside. This unique structure allows grease to adhere to vertical surfaces, resist water, and seal out contaminants, something conventional oils cannot easily achieve. In other words, grease is basically a gel-like sponge that stores oils and additives while delivering lubrication exactly where it is needed. But how did this chemical combination emerge? The history of grease is a journey of human ingenuity against friction and wear. Ancient civilizations already struggled with lubrication problems thousands of years ago. Egyptians and Romans used mixtures of animal fat and lime to lubricate wagon axles more than 3,000 years ago. However, the real breakthrough came during the Industrial Revolution. In 1853, English inventor John Ellis was experimenting with cottonseed oil to treat locomotive components when he accidentally discovered that mixing it with calcium hydroxide created a paste resistant to heat and vibration. His patent marked the birth of modern grease. The next major leap happened in the 1930s, when researchers at Saucony Vacuum Oil Company, which later became Mobil, developed the first lithium-based grease with thermal stability 5 times greater than previous formulas. This discovery was revolutionary because of its molecular structure. Lithium hydroxystearate forms crystalline fibers that create a stable three-dimensional network capable of retaining oil even under high temperatures and heavy mechanical stress. Today, according to the National Lubricating Grease Institute, nearly 70% of all grease produced worldwide still uses lithium as its foundation. But how do manufacturers transform liquid oil into this metallic gel? The process is a carefully controlled choreography of heat, chemistry, and timing. In the production of simple lithium grease, fatty acids react with lithium hydroxide in water at around 100 degrees Celsius, forming a metallic soap. Mineral oil is then added, and the temperature is raised to approximately 200 degrees Celsius to dissolve the crystals. The secret lies in the slow and controlled cooling process. As the mixture cools to around 150 degrees Celsius under agitation, soap fibers crystallize and weave together into a microscopic network that traps the oil. For more demanding environments such as steel furnaces or spacecraft, manufacturers create complex greases by adding compounds like benzoic acid, allowing the grease to withstand even higher temperatures. The type of grease selected depends entirely on the operating conditions because different machines experience different forms of friction, contamination, pressure, and heat. And when soap-based chemistry is not enough, engineers turn to non-soap greases. Instead of metallic soaps, these formulations use inorganic or organic thickeners. Bentonite clay, for example, can be dispersed into hot oil to create greases capable of resisting temperatures above 200 degrees Celsius without melting, making them ideal for furnace bearings. Polyurea greases, created by reacting diisocyanates with amines directly inside the oil, produce highly durable polymers capable of lubricating wind turbine bearings for more than 15 years without relubrication. But where do these formulas face their greatest challenges? This is where tribology enters the picture. Tribology is the science of friction, wear, and lubrication between moving surfaces. In underwater mining operations, calcium sulfonate greases must repel saltwater while resisting pressures equivalent to thousands of atmospheres. In aviation, fluorosilicone greases lubricate landing gear mechanisms at minus 54 degrees Celsius during flight while enduring temperatures above 150 degrees Celsius during braking after landing. Even space exploration depends on advanced grease technology. Spacecraft such as NASA's Perseverance rover use PFP-based greases, known as perfluoropolyether lubricants, because they do not evaporate in vacuum conditions and can survive intense cosmic radiation. So, why use grease instead of oil? Grease becomes the ideal solution whenever four conditions exist at the same time: the need for retention against gravity or vibration, sealing against dust or water, long-term lubrication with minimal maintenance, and resistance to extreme temperatures, pressure, or chemicals. In automotive CV joints, for example, lithium complex grease withstands centrifugal forces exceeding 500 times gravity, where ordinary oil would be expelled almost instantly. In cement mill bearings exposed to abrasive dust, grease acts like a chemical bodyguard, protecting the surfaces while maintaining lubrication. Choosing the correct grease for each application depends on several important parameters. One of the most critical is NLGI consistency, which measures hardness. Lower grades are more fluid, while higher grades are more solid. High-speed bearings typically require softer greases to minimize internal friction, while heavy open gears demand softer penetrating formulations capable of reaching narrow gaps. Another important property is the dropping point, which indicates the temperature at which the grease structure collapses and becomes liquid. Additives also play a major role. Molybdenum disulfide improves performance under extreme pressure, PTFE reduces friction, and silicone-based compounds increase water resistance. Using the wrong grease can be catastrophic. This is why modern science continues to push lubrication technology even further. Researchers are exploring materials that challenge conventional physics. Nanographene additives can reduce friction by up to 40% by forming self-lubricating molecular films. Ionic fluid greases survive extreme vacuum conditions and ionizing radiation without degrading. Systems such as SKF SmartLube allow industries to maximize equipment reliability while reducing downtime and maintenance costs.